Okay, so next one is Tolu. He's a PhD student from UC Davis, where she's advised by John Owens. She has also enjoyed the mentorship from multiple people, including Fletcher and Emer. She completed her undergraduate degree at the University of Toronto. Then she moved to Silicon Valley, worked at Microchip, and then started her PhD program. Today, she's going to be talking about accelerating sparse data orchestration via dynamic reflexive tiling.
Thank you. All right, that's it. Okay. So, hi everyone, I'm Tolua, and I'm excited to share with you our work on dynamically tiling sparse computations. Let's continue on this theme of sparsity from our previous speaker and start with a quick primer on sparse tensor algebra. So a tensor is a multidimensional array of 1D, 2D, or 3D data, and so on. And when that data contains very few non-zeros, it becomes a very sparse tensor. We can exploit this sparsity to save on memory storage by compressing the data into a representation such as CSR. So now accessing data requires touching both metadata and data. Sparse tensor algebra involves a series of binary operations between tensors, some of which are sparse. We focus on sparse tensors in a range of less than 1%. These are found in applications such as graph algorithms, recommendation systems, and computational chemistry. These applications often deal with multiple sparse operands, such as the previous example we had of sparse-sparse matrix multiplication. This is used in applications like multi-source breadth-first search or in sparse linear solvers. Due to these matrices having low density, irregular sparsity patterns, and a need to access both metadata and data, performance of these kernels is memory-bound and computation is load imbalanced. So there is a chance for performance improvement if memory is accessed more efficiently. So this is an opportunity even for state-of-the-art sparse accelerators in this domain. As we can see here, the amount of memory traffic they induce over a collection of benchmarks is significantly higher than the ideal memory traffic, which would be reading and writing tensors once. To summarize, and speaking more broadly, the challenge with sparse computations is they are memory-bound, so we need a more efficient use of memory bandwidth. And we talked about SPM, but a large number of kernels exist that have multiple sparse operands, so we need something that's general regardless of the kernel. And speaking of accelerators, there are a wide variety of them, so we need something that's ideally portable regardless of the platform. So to capitalize on these opportunities, we developed dynamic reflexive tiling, or DRT, a portable algorithm and hardware mechanism that improves memory usage efficiency of sparse tensor kernels. So DRT improves efficiency using tiling. Tiling is an optimization that improves memory usage by improving data reuse. So let's briefly overview how tiling works for dense problems. We'll use matrix multiplication as our running example, and tiling works great in this setting. So each of these tiles are filled with 4 non-zeros each, if we assume that our buffer storage requires each tensor to have 4 non-zeros. This enables data reuse, increasing how much we use the data for compute once it's brought on chip. When we improve data reuse, arithmetic intensity, the amount of compute per byte transferred, increases, and the memory traffic decreases. If we did the calculation, memory traffic is actually cut in half through tiling alone in this example. So what if we try to apply this to the sparse world? Here, we're now sparse, but notice the tiles are no longer full. The number of non-zeros in the tile is no longer equal to the 2x2 tile shape that we have. So this decreases the data reuse. Additionally, tiles have different numbers of non-zeros in them. For example, A00 and B00 have occupancies of 3 and 1 non-zeros each. Meanwhile, A11 and B11 have occupancies of 1 and 1 each. This will lead to load imbalance if we parallelize on these pairs of tiles. And by the way, Extensor, which is a prior state of the art in sparse tiling, does this approach and still uses memory inefficiently. What we need is a sparse tiling strategy that allows us to successively successfully achieve data reuse. So we make three key observations to adapt tiling for this. First, tile shapes must be non-uniform. Second, tiling needs to be done in the so-called coordinate space. And finally, our tile shapes must be created dynamically or at runtime. So let's break these down. So as we just saw with the static tiling example, sparsity is irregular, and uniform shapes, where all tiles within a tensor are the same shape, lead to variable tile occupancy. So we need a tiling option that lets us choose, in the best case, non-uniform tile shapes such as these. These tiles now have as high as occupancy as possible to maximize data reuse, subject to the on-chip storage constraints, and these tiles have as equal a number of non-zeros as possible to minimize load imbalance. Whereas the state-of-the-art tiling approach in this example gives us 2 non-zeros on average per tile, this ideal non-uniform tile-shaped matrix gives us 4 non-zeros per tile. But we can't choose tile shapes in isolation. We need to consider the other operands in the tensor kernel. So this is both A and B in our matrix multiply. Specifically for the shared dimension of K, the coordinate range of tiles from A and B along the K dimension needs to match. So the A00 tile from A will produce these tiles in B. But note that while we need to do this, it creates a challenge. Due to the shared dimension constraints, we might create small low reuse tiles. For example, while A has a perfectly set of chosen tiles, B03 has only one non-zero in it. So we need to be able to maximize reuse across all operands. And finally, the tile occupancy depends on the sparsity pattern of participating operands, which we only know at runtime. The tile shape may change depending on what region of computation we're working on. So for example, if we had computation with this first 2 tiles of A, B is going to have these tile shapes. But for this region of A, the tile shapes in B change. For a given region of data in a matrix, the tiles that correspond to that data for that matrix are going to change based on the parts of the other operand that we're working on. So we can only know this at runtime. So at a high level, the parser of the art applied dense tiling to sparse workloads, and we can call this static uniform coordinate, or SUC tiling. But what we actually need is dynamic, non-uniform, coordinate-based tiling. But this DNC tiling scheme requires a search over all possible tile shapes, subject to the constraints that shared dimensions across operands are the same, and that you don't overflow any of the storage that you have. So clearly, this is going to be really expensive. So to address this, we propose an algorithmic framework which we call dynamic reflexive tiling. In this algorithm, we simplify the search process by specifying heuristics to greedily grow tiles, 1 dimension at a time, according to the data flow. The tile shapes are coordinated across operands. The system we're working with is an extensor-like accelerator, where we added a hardware unit, the tile extractor, which implements DRT in hardware to further speed up the process of finding the best tile shapes. For further details on this, please check out our paper. And this tiling can also be applied hierarchically, such that DRT tiles between DRAM and the global buffer, then between the global buffer and the PEs, distributing the tiles. As an example, let's assume our computation holds A stationary with this loop nest ordering of M, N, M followed by K followed by N. And we can visualize the computation space on your left here. DRT grows tiles while walking this computation space. So since we're A stationary, we start by growing tiles along A. For this example, let's start with a 2 by 2 tile, which covers these points in the computation space. Now let's grow K as much as possible before growing M. Note that other strategies are possible. DRT allows you to alternate between growing K and M, or start off with a different tile shape as your starting point. Growing by 1 on K, our buffer is now full with 4 non-zeros, so A is done. Since A is fixed, we can now grow B. B is constrained by the K dimension of A, but can still grow along N, so we're going to grow along N by 1. until the buffer hits 4 or less than 4. Once a pair of tiles is formed, we send that pair for computation to the next level of the memory hierarchy. And so we continue creating tiles along n, growing by 1 until we cover all of the n dimension in our loop nest. So we want this entire region of the inner loop nest to be covered. Now, each of these 4 tiles will be paired with the A tile and sent to the next level of the memory hierarchy as 4 tasks. We can now continue the growth process starting from where we last left off in the loop nest at k equals 3. And growing on k, we get this new tile in A, and then we go to our inner loop nest again where B is constrained by A, and we continue growing until we get this tile. And we iterate through all of n, building tiles as we go that fill but do not overflow the buffer. So once we've covered all of n, and now all of k, we can now go back to our outermost loop nest of m and create a new tile at m equals 2. And again, we'll do this process until we've covered all of m, k, and n. So overall, DRT essentially greedily grows tiles while walking the coordinate space created by the loop order of our computation and meeting the buffer capacity constraints. But this process is still expensive in hardware since it requires reading every single scalar value. So we grow tiles in groups of microtiles, looking at larger granularities instead of growing by individual scalars. We're quantizing the tile growth. So to learn more about this, as well as our hardware implementation, please check out our paper. To test our tiling approach, we implemented a high-fidelity model of extensor and integrated DRT into it, and we call this integrated approach tactile. We tested over data from the Frost and Sweet Sparse databases and evaluated SPGEM and a higher order tensor kernel. And these are the matrix shapes that we evaluated for the SPM kernel. So does DRT successfully improve performance over the static tiling approach, or namely extensor? And the answer is yes. Here we have extensor's performance in blue, and in green we have tactile, which again is extensor with DRT integrated into it. Overall, tactile has a speed up of 3x over extensor, and this comes from the improvement in being able to do more compute for a given tile. This also corresponds to a memory traffic improvement ranging from 2 to 4 times less data traffic, depending on the kernel. I just showed you the results for a particular design, but what we're presenting is a general tiling approach. And so when we augment DRT into other architectures, here are the results. So the bars are showing the speed up over the idealized baseline accelerator when we integrate DRT into it, and the red dot is the DRAM limited speed up. That is the maximum speed up achievable given the arithmetic intensity. In all cases, DRT was able to improve these numbers. And this approach is also applicable to software. We implemented it as a software algorithm where arithmetic intensity improved by about 7x, and for higher order tensors, it improved by 16x and 3x over the tiling and untiled approach, respectively. So if we go back to our original figure that I showed at the beginning, DRT is successfully able to close this DRAM traffic gap in a portable and a general way. So I hope you check out our paper to further understand our implementation. Please contact me or meet me at the poster session later today if you have any questions.